Next up is Gert and Thomas from Flexoptix. Now, unfortunately, the fire department wouldn't let us do the full demonstration. So we're going to have to play a video so we don't set fire to the place, even if we leave a bottle, even if we leave the water there. So we apologize for the curtailed show.
We drink later.
Anyway, 800 gig and testing. Over to you, Thomas.
Thank you very much, Fergus. While Gerhard is preparing everything, actually he's finished already, perfect. My name is Thomas Weible, co-founder and CTO at Flexoptix, and together with Gerhard, our lead research engineer, I brought a topic to nog.fi where I think is quite of interest because it is about, we said reliability testing up to 800 gig. And the background of this talk is we make heavily use of the DSP later on the transceiver itself. But the reason why we do this is when you establish a link in your network, and then until 100 gigs so far, you basically were looking at the power levels if TX and RX is fine. Now, with the latest technologies on transceivers, you are also able to do bit error rate tests with those transceivers, which is pretty awesome. Then you can really look in advance, is the link error free actually? And that's what we want to show today. A little bit about the background and how it's done. Nope. So the talk is a little bit separated in a couple of sections. So we do first, we're gonna do a intro, a recap, and then we gonna look in detail about the temperature and also the distance. So these are influencing factors on the bit error rate. And then Gerhard is performing a live demo, plus we do some recap. So let's start straight out, more a little bit on the theory. We gave a talk, not here I think, but last year we went with a talk about coherent transceivers, and especially when you look on coherent side, you'll need to look and to be aware when you run DWDM, you need to be aware of signal to noise ratio. So what's the signal to noise ratio? You see it on the bottom graph there. It's pretty straightforward. We got our noise level down, which is the fuzzy wobbling graph, and then we get our desired signal on top of it, like here. And so basically the ratio is between this level, and the goal is to have a decent amount of ratio between the noise and the desired signal, because when this ratio is shrinking down, it's very hard for the receiver to distinguish if these are zeros and ones. Now, the signal to noise ratio is mainly, or it was introduced for DWDM folks, for the optical transmission people. And when you're coming more from the datacom and doing as a network engineer, which I assume the majority of the audience is a network engineering part, then actually the bit error rate is way more of interest. And we will show later on there is a relationship between the bit error rate and the signal to noise ratio. So we are mainly focusing on the bit error rate. When we turn back a little bit the time as well, back in 2019, the first 400 gig transceivers were introduced. And what is so special on those 400 gig transceivers? Actually, this is this tiny chip in there. Actually, it's a little bit a bigger one. It's a digital signal processor. So it was mainly introduced to hold functions like the gearbox, to convert from our multiple lanes on the electrical side to only a certain amount of optical lanes. So typically it was 8 to 4, 8 electrical lanes to 4 optical lanes, but also it does hold a couple of correction functions like the forward error correction. And for this talk now, we will mainly focus on the analysis of the bit error rate and the signal to noise ratio. And the O is the optical part, the optical signal to noise ratio. So what did we test? We did a couple of tests with a couple of transceivers, started with the latest one, the 800 gig development, it's a DR8, but also moved on with the 400 gig ones like the QSP112, which is a great development there, having 4 times 100 gigabit on the electrical side. And then as a side product, actually, out of the 400 gig development, the 100 gig transceivers also got a DSP now. And with the 100 gig transceivers, you have the great benefit, you have a single lambda transmission. So it's not 4 lambdas or 4 wavelengths coming out of the transceiver any longer. So it's just one wavelength. We add there some modulation to get everything squeezed in. But the nice effect is we have one wavelength carrying 100 gigabit. And yes, we need a DSP there to do the modulation especially. Okay, so as I said, we did a test at the beginning with on the distance, and we're going to show you the results. We only have chosen one result. We had a couple of results, but this will extend this talk way too much. So our setup looked pretty straightforward. We took a 100 gig QSOP28 ER4, which is capable to go for reach up to 40 kilometers. And then we used a couple of attenuators and also some fiber drums or cable drums, cascaded them in distances of 10 kilometers and 20 kilometers. And we basically looped it backwards. So the transmitter was looped to the receiver. And this was basically the test setup. Looking at the figures, we just stick to the data sheet and we're looking especially on the receiver's minimum, which is at -14 dBm, which you can see here in the red rectangle. And this -14 dBm is quite important because you will see later on in the result, this becomes crucial. We added attenuators there because we wanted to be really at that edge and also didn't want to overload the receiver because there's also a maximum receiver value which you don't want to exceed. Okay, so these were the results. So we were running the bit error rate test straight on the transceiver itself, and we pulled out all the data on a certain time, but also monitored the temperature. And for 2 meters up to, let's say, 40 kilometers, the figures look pretty nice. Some words about the bit error rate itself. So there is a demarcation line, the 2.4 multiplied by 10 to the power of -4. And for simplification, I just use the exponent now, and when I'm talking in the future, it's -4 basically. This is the demarcation line, which is defined by IEEE for an error-free transmission. If you're above, then your link is not error-free any longer. And the interesting part is, yes, 50 kilometers was way above, so we were out of spec for sure. And the 20 kilometers quite of interest. It was close to the edge of, to the power of -4. And when we look at the green rectangle there, we actually could identify that this was the worst RX power level we had, not taking the 50 kilometer in consideration, this was even worse. But we were really at the maximum or at the minimum receiver's sensitivity at -13.4 dBm. And yeah, you might wonder about those jumps with the question mark. This is more an implementation thing of the bit error rate function itself, and especially about how the laser is control of that transceiver. So when the temperature exceeds the TX, the transmitter bias, is going to be corrected. It's basically a lookup table in the firmware of the microcontroller to change some settings on the bias, and then the bit error rate got improved, so it was always a drop down and not a drop up actually. Okay, as I said before, a little bit more theory about the bit error rate. So what is the bit error rate in general? You have a number of errors when you're transmitting, and you divide this by the total amount of bits you transmit in a certain period of time. That's basically the whole formula you have to do, or actually the chips or the computers inside of your router, or in this case, the transceiver does it for you. And just be aware, when we do an example with 100 errors on a 100 gigabit link, and we assume a complete error-free transmission of to the power of -12, which is error-free actually, then the gating time between the errors is roughly 16 minutes, which is pretty awesome. So every 16 minutes you encounter an error. Now, when we get down to this demarcation line, which is defined by IEEE, to -4, the gating time is 4 microseconds. So every 4 microseconds an error will show up. So now you can see what the forward error correction basically does to get an error-free transmission, getting down to or up to -12. There's a lot of calculation and math involved there. Moving on, we did a second setup, now looking more on the temperature side. And for this scenario, we just used the Flexbox as well, accessed the transceivers, DSP and microcontroller via the management interface. But we were facing some issues on the temperature, so we needed to add a heatsink there, just placed it on top of it. We got rid of the housing because this was important and added an external fan. The nice side story here is actually this heatsink, actually we got it from an old Cisco 800, so it's like 25-year-old technology is cooling down a coherent transceiver, which was pretty amazing. And we got it from a friend of mine. He is decommissioned equipment in Frankfurt area, and he rips everything apart and separates all the different materials. He really likes it. And if you have some equipment in Frankfurt area, let me know. I can help you to get rid of it. Okay, with that, I'm gonna hand over to Gerhard.
Anyhow, same diagram like before, but the difference this time is it is a coherent transceiver. And as you can see, we don't have jumps anymore. So the thing is, even though the coherent transceiver is way more complex, way more parameters, considering polarization and so on, it has the opportunity to control better the target power. And what you can see here in the result is that it is not so much affected by the temperature. So if you start your coherent transceiver with the proper cooling installed, like shown in the previous picture, you can see the temperature really doesn't affect so much the bit error rate. For one thing. For another thing, we are in a different range because there's a different specification, because the FEC also, because it has more parameters, is way better in correcting. So as a message, coherent, you can trust more on it if the temperature increases, that you will have more or less a constant bit error rate. The bit error rate obviously changes if you use different fiber lengths up to 60, and there's also a difference if you do it without cooling. We did it for a couple of minutes, and as you can see, the curves now moved. This is due to, because it locks to a certain power, target power, and then it keeps running that way. So to wrap up a little bit the difference between a direct detection transceiver we saw previously and a coherent, that is how they behave basically. And now let's go to an experiment. Let's go extreme, because edge cases are normally more interesting. And we came up with ideas, since we have all these triggers around 80, 90, 70 degrees. Let's put a transceiver up to 120 and see how it will react. Will it recover itself? How's the bit error rate, obviously? But in general, how does this transceiver react? And I did it through a small barbecue. You can also check out our YouTube channel. There are more details what exactly we were doing. I did it in 4 phases. So first was a warm-up. Without that dryer, it's not a hair dryer. It is one that goes up to 600 degrees. Don't use it for anything else other than for electrical devices. And warm up, let it warm up a little bit without that gun. Normally our application stops the transceiver when the temperature increases way too much. So I was waiting for that and seeing if it still works and how it reacts to the transceiver, if it can read out the register properly, because this is also something you can read out of a register. And after that, I removed this threshold. I put it to 100 in order to see how it reacts. So we passed the high warning, high alarm you can read out of the register. This is something you can also find your network gear. It's in the register of the transceiver. And when we did that, I tried another step with 120 to see if it still reacts, if it is able to operate, because I mean, you would assume that with 100 degrees, who knows what happens? I already got loss of signal, and yeah, will it still work? And it still was working, so I left it running up to 120, canceled the operation, and I was checking with the cooldown if it still works, and surprise, surprise, it still is working. So you can go way beyond. You're losing signal, but the transceiver was able to recover itself. Actually, we are not so proud about this experiment because we hoped we would really break this one. It wouldn't work at all, but it also shows us how reliable these transceivers are. It still doesn't mean you should just leave them running in hot and remove the fans. Of course, that not, because you lose the signal. You don't want that. But there's a probability that they recover themselves, because as you can see here with the curve, it goes back to the original bit error rate we had before. So this is a long run test just to see how the bit error rate behaves. Here we have 1.0, 10 minus 11, 10 to minus 11. And as you can see, it stabilizes, goes like 60% up, but after 4 minutes and then it keeps running at the same level of bit error rate. This is due to because we have a rolling average. Just to give you another example, what happens when you add a cooler or you remove it. Same here, temperature increases if you remove the cooler. But what does not recover entirely is the bit error rate. This is a blue curve here because rolling average. So it's taking history. It's always taking the past value. You know, you take the current bit error rate, sum the next one, divided by 2. And it does this in the background every time, the firmware of the transceiver. And this is the effect you start observing. If you reset the transceiver, plug it out, plug it in, or trigger and register, it also will go down. Just wanted to show you that because while you are running a transceiver, if you fix anything in your network gear, like putting a cooler back, this is what can occur. And now let's get to the interesting part. Have to rush here a little bit, but that's all right. To show you some interesting curves here. Click. Yeah. Now the transceiver is booting up. Let's give it a little bit of time while I explain what you are going to see here. So we discussed the bit error rates. This is what you're going to see in the first graph. The second one, temperature, obviously. RX power is like in order to verify the reception signal, how good it is. And media SNR is the signal to noise ratio. Like on the first slide you saw, this is the value we are measuring. It's usually a value that goes between 20 dB and 30 dB. That's what you expect. And yeah, still waiting to boot it up. It takes a bit of time. That's normal. But in the background, it's already running and it's throwing in the data. And as you can see with the bit error rate, yeah, it starts on 0, which is perfect. But since we haven't measured any bits, there are no errors to measure. But then it starts to detect some errors in its counter. And yeah, it's showing that temperature goes up because the transceiver, the DSP on it, is working. And RX power, obviously, it's pretty much downscaled, and we have a normal SNR. Now, in order to show you that this is not a replay, let's bend the cable a little bit and see how it reacts. And as you can see, it goes down. A usual value you can expect if there's almost no signal. The lowest signal you get usually is 40 dB. Here we go. Here we have it. Bit error rate goes to 1. So pretty bad. Everything is an error. And the media SNR also goes up. It's a good signal to noise ratio. This is usually a value our supplier put because it means that is outside of the range. You never go beyond 30 dB, so that is the specification. So if you see something like that, it is bad. If it goes below 20, it's also bad. As you can see, there are jumps. But now I left the cable, it is all good. It recovers itself somewhat. Here you can see the curve with a bit error rate, it goes down. Now it's like upscaled a lot, but you can see this effect here as well. Yeah. Another effect we have here around is the FPS, the frame per second, as you can see, is not as smooth. This is due because media bit error rate and SNR are shared. So we read from this transceiver by swapping out with the diagnostic bits the values, but we can disable this if we do it. You start up seeing it a little bit smoother and it's running a little bit faster. So now I'm only recording the current bit error rate, temperature. I could do the same with the media SNR, but it's a small prototype just to show off how transceivers react and interact with your network gear, right? Okay. Let's go back to the presentation. A couple of seconds are left. Yep. 250 degrees. We did it because we really wanted to see how far we can get. And this is how the transceiver now looks like. You cannot even read the label. I added another graph here, the weird point, which is 128, because it's an unsigned char, so the last bit is the signed bit. So if you go beyond 128 degrees, you start seeing negative temperatures that are unrealistic. They don't go below 0 Kelvin, but you know, well, 1 bit. And I had to correct it, which I did. The signal was lost. I'm not showing you the whole diagram, but I can assure you this transceiver doesn't work anymore. A very bad signal. And yeah, wrapping it up a little bit. You saw the direct detection transceiver PAM4 diagram, how it corrects and has its control circuits, and you start observing jumps. Bit error rate, no matter which transceiver you use, is a rolling average. And there isn't that much margin between higher alarm temperature and loss of signal. So keep an eye on those. They are very important. And Thomas,
yeah,
coherent.
Maybe some words about the loss event, which Gerhard showed on the graph when he did the high temperature test with the 120 degrees. This was actually an artificial loss. So we saw there was a shutdown of the laser at 80 degrees, and this is more of a safety function of the DSP itself. So what the DSP did then was, okay, I'm way too hot, I'm gonna shut down it now, and then you will look at your link anyway because the link is gone. Otherwise it would have been broken. Furthermore, on the coherent side, the coherent signal itself is a little bit more ruggedized. It makes way more use of the properties of light. Instead of just looking at the amplitude, we do have polarization, we do have the phase, and the combination of those make the signal way more ruggedized. And there we were able to see temperature changes do not matter that much, but don't get me wrong, high temperatures, when we exceed the specs, for sure it will influence it, but just the changes were not that big issue. And finally, as said at the beginning, there is the signal to noise ratio, and we still can leave it to the optical transmission folks to do the DWDM stuff, because there is a close relationship between the SNR and the bit error rate. So when your SNR is good, or your BR is good, that way around, then you don't have to worry much about the SNR, because they are really correlate with each other. Okay, that's it from our side. Thank you very much, and we are happy for questions.
Thank you. Thank you, Thomas and Gert. We've run into the coffee break, so unless somebody has a really, really quick question, can I suggest you catch them, and you'll be here for dinner?
Yes, for
and
sure.
so
We're going to be around,
yeah,
definitely.
So,